Hello and welcome everyone. In this session, I am going to talk about FFA compliant secure user mode partition, where the partition manager exists at EL3. In the past, there has been talks and significant amount of work around having secure partition manager at Secure EL2 or at Secure EL1. This talk is focused more on introducing the FFA compliant Secure Partition Manager at EL3. Firmware framework architecture for ARM v8 platforms, also known as FFA, defines a spec which standardizes the communication among normal world and secure world images. In this talk, we will cover the objectives behind this proposed model, the existing solution, some key features about FFA, and the proposed model, and in brief, how it works. I, Sayanta, will present the topics, and my colleague Aditya will be present to take questions post presentation. The key objective for this implementation is to have an out-of-box secure software solution for ARM platforms that do not support Secure EL2, which is like pre 8.4 version, or do not deploy any secure hypervisor at Secure EL2. Also, the platforms that do not deploy a secure OS at Secure EL1. Overall objective is to have a secure software solution following firmware framework architecture for ARM v8 platforms. At present, SPM-MM is the existing solution, where SPM-MM acts as the secure partition manager, and it is part of trusted firmware at EL3. SPM-MM manages the context of secure partition and communication among normal world and the secure world images. StandaloneMM acts as secure partition, which executes at secure EL0. On the normal world side, there is MM communicate, which is part of EDK II, and the normal world firmware and the secure partition communicate using MM interface IDs. The current solution looks like how it is shown in this picture. The firmware framework for ARM v8 platforms standardizes the communication among normal world and secure world images. The spec defines a partition manager concept which manages the resources for all partitions and ensures inter-partition isolation at runtime. There is also a concept of partition manifest, which is to hold all the configuration data of the partition, and it's an implementation defined method. It could be of any format. One of the example could be a device tree, where partition specific configuration details can be captured. There is a list of extensive application binary interfaces for various purposes, such as discovery of partitions, direct indirect message communications, memory management operations, and even CPU cycle management operations. These are some of the key features defined by the FFA spec. Going into a bit more detail about the partition manager, FFA spec splits the secure partition manager into two components. One is dispatcher, known as SPMD, and another is the core, which is known as SPMC. SPMC is the component which initializes and manages the partition resources and ensure all the isolation amongst them. And FFA spec allows SPMC to be included at any of the exception level. It could be either at EL3 or at Secure EL1, or it could be at Secure EL2 on platforms which support Secure EL2. So there has been work on the front of having Secure EL2 Secure Partition Manager or Secure Partition Manager at Secure EL1. And but this talk is more focused on introducing a model where SPMD and SPMC both coexist at EL3. And this choice of including the SPMC at particular exception level is done based on the platform architecture and the project requirement. So the model with SPMD and SPMC both at EL3 looks similar to this, how it's shown in this picture. The proposed model with users secure partition and SPMC and SPMD at EL3 looks how it's shown in this picture, where SPMD and SPMC both are part of trusted firmware and are at EL3. StandaloneMM is the secure partition and executes at secure L0. Shim layer is sandbox between StandaloneMM and trusted firmware, which is a bare minimum code and just helps in changing the exception level. On the normal world side, there is MM Communicate, which is part of EDK II. As part of this implementation, SPMD at EL3 has been modified, and on the EDK II side, MM Communicate and standalone MM modules are modified. SPMC module has been introduced at EL3, part of trusted firmware. And also for better code reusability, SPM-MM code has been modified and reorganized so that some part of common code can be used by both SPM-MM and SPMC. Going into a bit more details about the FFA changes on the EDK II, MM Communicate is the module exists at EDK II, which allows normal world components to communicate with the secure world via spec-defined SMCs. StandaloneMM, which is loaded by EL3 firmware, executes as secure partition in Secure EL0 on ARM Arc64 platforms. So the changes in StandaloneMM and MM Communicate for FFA support are similar in nature. So FFA support for handling direct message communication and SPM version checking, error responses have been added in both places. And there has been a built-in option introduced for user to choose to opt either existing MM interface or the FFA interface for communication between normal world and the secure world images. On some more details about the Secure Partition Manager work for this proposed model, SPMD module is the gateway for handling any FFA SMCs either from normal world or secure world, and it forwards the SMC request to SPMC. And since SPMC coexist at EL3, SPMD doesn't need to handle any exception level change, but it's just a SPMC module function call. So far, the SPMD was handling the cases where SPMC is either at Secure EL2 or at Secure EL1. So under those designs, SPMD had to manage the exception level change, but after inclusion of SPMC at EL3, and in this model, SPMD will just have to make a SPMC module specific function call for handling the FFA SMCs. SPMC is the one which initializes and manages secure partitions. It gathers memory region details, prepares memory mapping, and creates translation table out of it, and it creates the execution context for user partition. And during handling of FFA request, SPMC does the job of saving and restoring execution context and jump to respective exception level. The SPMD, SPMC, and secure partition setup routines are shown in this picture in bit detailed way. So SPMD setup routine is the first one to kick in. So it initializes the SPMC context array for all cores and invokes SPMC setup routine. SPMC setup routine invokes the secure partition specific setup routine. Secure partition setup, it will first get the partition specific boot arguments, memory region details, and create memory mapping and translation table out of it. And it prepares the CPU context for StandaloneMM, which is the secure part, user secure partition in this case. Once setup of the secure partition and the preparation has been completed, it will return back to the SPMC setup routine, and there it will register a secure partition init routine and returns back to the SPMD where the setup functionality completes. And once the secure partition init routine is invoked, it will try to make a jump to the user level by making a function call, and where the runtime EL3 context will be saved and an exit will be made to the secure user mode. So here the StandaloneMM init routine will be starting, and as the first step, the boot arguments will be parsed, and it will fetch the booting structure out of that. And as part of peak of image, it will have a requirement of getting or changing the memory region attributes at boot time. On doing so, STMM will make FFA direct message ABI request to the Secure Partition Manager, which has the authority of manipulating the memory region attributes. So after receiving the FFA direct message request, SPMD will forward it to the SPMC, which will look into the request and do handle accordingly. It may it may get the memory region attribute details, or it can change the memory region attributes. On completing the function, it will return back, and it will return back to the secure partition by responding through FFA direct response ABI. So this FFA direct message request and the direct response uh, ABIs, this way of communication will iterate few number of times as part of the boot process. So once the SPMM booting process completes successfully, it responds back to the Secure Partition Manager by using the FFA direct response ABI. SPMD will receive the direct response request, and it will forward it to the SPMC. On receiving the response, SPMC will understand the secure partition booting has been completed successfully, and it will try to save the secure partition context, and it will restore back the runtime EL3 context, which was saved before starting the secure partition init routine. So this way, the SPMD, SPMC, and secure partition setup routine completes by using FFA ABIs. UEFI Secure Boot is one use case which is covered by using this proposed model. So on the normal world side, there is as part of EDK II, it has a feature of secure boot. If enabled, the secure boot framework performs a lot of secure boot related jobs, and as part of that secure boot process, it requests for secure keys through Communicate using FFA direct messaging APIs. After this direct messaging API request has been placed, SPMD module will receive the FFA direct message APIs from non-secure world and forwards the request to the partition manager core, which is SPMC. SPMC module saves the normal world context and prepare the payload for FFA payload for jumping into the secure user partition, and it prepares the context for jumping into the secure partition. Once the change of exception level is done and the request reaches secure partition, which is StandaloneMM in this model. So the secure partition also has access to the secure storage. So the platform where this use case has been verified, NOR-Plus acts as the secure storage, and secure partition has access to the secure storage. So as part of its booting process, it initializes the interface for accessing the secure storage. So after receiving the FFA direct message request for secure key information, it will access the secure storage and get the key information. After receiving the key information, it will copy into the FFA payload buffer and respond back using the FFA direct response API. So after the FFA direct response API received by SPMD, it will forward it to the SPMC, and SPMC will pass on the payload message and restore the normal world context. And thus the normal world routine in the communicate and EDK II will resume. The way of communication between normal world and secure world for getting the secure key information will continue for a number of iterations as part of the secure boot process, and this will use the FFA interface. So by this method, the UEFI Secure boot will uh, complete, and it will use the FFA APIs in that process. On current status, the StandaloneMM FFA interface support has been already added by upstream community, and it's merged as well in the EDK II upstream code base. FFA support for is added in the communicate for interaction from normal world. Interested firmware changes are made in SPMD and SPM-MM to accommodate newly introduced SPMC module. At present, only direct messaging ABIs are implemented for communication between normal world and the secure world partitions. UEFI Secure boot is one key user scenario which is covered with the current implementation. Next, very immediate objective is to get all the changes and solutions merged into the respective upstream code bases. On feature opportunity, uh, the the effort will be to engage with the community and encourage on covering larger number of use cases, and thus supporting more number of ABIs. Yes, that would be all we had to present about.